In this problem, we have a battery. The EMF of the battery is given, and our battery has some internal resistance, which is also given. It's connected to a light bulb, and the question is, what percentage of the power delivered by the battery is dissipated by the internal resistance of the battery, and it's not available to the light bulb. Mathematically, this is what we're looking for. Power dissipated by the internal resistance of the battery, that I call P sub lowercase r, divided by the power delivered by the EMF, and I call that P sub script E. So what is this equal to? If you think about it, the power delivered by the EMF is equal to the total power dissipated in the entire circuit. So that's what I'm going to do in the next step. So here I have replaced the power delivered by the EMF with the power dissipated in the entire circuit. I'm using subscript capital R plus lowercase r to denote that this is the power dissipated by the light bulb plus the power dissipated by the internal resistance of the battery. Now let's remember the formula for power. Here's the defining formula for power for any circuit element. Power is equal to current passing through the circuit element times the voltage across the terminals of that circuit element. Now, in the case of a resistor, we can combine this formula with Ohm's law to come up with an expression for power that only involves current and resistance, like so. According to Ohm's law, the voltage across the terminals of a resistor is equal to the current passing through that resistor times its resistance. So V equals I times R. I'm going to substitute this back in the power formula to eliminate V from the power formula. And here's what I get when I combine the two formulas. Power for a resistor is equal to I squared times R. It turns out this version of the power formula is more convenient to use in this problem. Why? Because if you think about it, look at the circuit. It's a single loop circuit, and there's only one current passing through everywhere in the circuit, right? Whatever that current is, let's call it I. The same current is passing through the light bulb, and the same current is passing through the internal resistance of our battery, so that I in the power formula is common to both. Now let's go back to our initial equation for the ratio of the powers and substitute this definition of the power formula. So here it is. The ratio that we're looking for is the power dissipated by the internal resistance divided by the power dissipated by the light bulb plus the power dissipated by the internal resistance. Now we have I squared in every term, so I squares cancel. And this is what we get after the simplification. Now let's go ahead and plug in the numerical values and calculate. Here's the numerical result. So 7.16% of the power delivered by the EMF is dissipated by the internal resistance of the battery, and the rest of the power goes to the light bulb.